While you're watching this video, whether you're standing on the bus and holding your phone, or sitting at your desk and watching from your computer, I want you to try something with me. If you're able to, try wiggling your toes. Was that pretty easy? Now try scratching your nose. Still pretty easy, right? But imagine never being able to do that. Imagine never being able to get on the bus or hold your phone. Imagine never being able to wiggle your toes or really scratch that itch. That's a reality for over 300,000 North Americans and 20,000 more patients every year that can't get on the bus, they can't hold their phones, or they can't wiggle their toes or scratch that itch because of a spinal cord injury. That's 6 times the population here at the University of British Columbia. I want to tell you a story that happened very recently. 3 months ago, a close family friend of ours was in an accident. My friend's dad, Chris, looked like this patient. He has a spinal cord injury and he's paralyzed from the neck down. Unfortunately, the doctors weren't able to accurately diagnose him. And in order to diagnose a spinal cord injury, we need a patient to physically tell us if they can move certain muscles or feel certain sensations. And those sensations include the anal region. It's an incredibly invasive exam. Do you think Chris, in a state like this, can move any muscle or talk about any sensation he has other than pain? And so I spent a lot of time trying to figure out, how can we better diagnose patients like Chris? Specifically, I'm trying to find some signal in the blood called a biomarker that can tell how injured the spinal cord is. And biomarkers are quite common if you think about high body temperature, that's a biomarker for fever. High blood pressure, that's a biomarker for stroke. So for spinal cord injury, I study tiny pieces of genetic material called microRNA. Where DNA is like the whole blueprint to life, think of microRNA as the body's text messages. When the spinal cord is injured, it instantly releases microRNA into the blood where we can detect them. Think of an oil tanker that runs into a rock. Initially, we don't know how bad the damage is, but we could get a pretty good idea based on how much oil has leaked into the ocean. Similar to this, I can identify how injured the spinal cord is by measuring the amount of microRNA in the blood. And in our lab, we're very fortunate to have the world's largest collection of blood from patients with spinal cord injury. And I use these samples to profile thousands of microRNA molecules using the same technology that we use for the Human Genome Project. That's called next-generation sequencing. And so far, I've identified a set of microRNA that seem to be more predictive of outcome than the current tools that we're using. And I'm hoping to use these and validate them in trauma centers across Canada so that patients like Chris can get accurately diagnosed, effectively treated, and maybe one day Chris can wiggle his toes or scratch that itch.